Beyond Earth's protective magnetosphere, an unseen torrent of energy constantly bombards the cosmos. Galactic Cosmic Rays, particles accelerated to near light speed by distant supernovae, traverse interstellar space, posing an existential threat to unprotected biological systems. This pervasive, silent hazard defines deep space endurance, demanding a fundamental shift in astronaut protection strategies. These high-energy particles, predominantly atomic nuclei, possess immense penetrating power, capable of tearing through spacecraft hulls and human tissue. Unlike transient solar flares, GCRs are a constant, isotropic threat delivering cumulative damage over extended missions. Their interaction with biological matter creates cascades of secondary radiation, amplifying cellular destruction and compromising long-term health. Conventional shielding relies on mass, typically water or dense materials, to attenuate radiation. However, the sheer quantity required to effectively block GCRs renders long-duration deep space vessels prohibitively heavy and impractical for propulsion. This engineering paradox necessitates innovative solutions that transcend physical barriers, pushing scientific inquiry towards intrinsic biological resilience. The frontier of space survival is shifting towards bioengineering, the deliberate modification of living systems to enhance their robustness against environmental stressors. This approach aims not merely to deflect radiation, but to fortify the astronaut at a cellular and molecular level, transforming the human body into a more resilient biological entity capable of enduring the cosmic environment. One primary strategy involves augmenting natural DNA repair mechanisms. Cosmic radiation inflicts direct and indirect DNA damage, leading to mutations and cellular dysfunction. Bioengineering seeks to upregulate specific repair pathways like non-homologous end joining or homologous recombination, making cells more efficient at mending radiation-induced breaks and lesions, thereby preserving genomic integrity. Furthermore, enhancing antioxidant production within astronaut cells can mitigate the indirect damage caused by reactive oxygen species, ROS, which are byproducts of radiation interaction with water molecules. Genetic modifications could boost the endogenous synthesis of powerful antioxidants, neutralizing free radicals and reducing oxidative stress that would otherwise contribute to cellular aging and disease. Another avenue explores the transplantation of radiation-resistant genes from extremophile organisms, such as Deinococcus radiodurans, known for its extraordinary DNA repair capabilities. Integrating these genetic sequences into human somatic cells could confer a heightened tolerance to radiation exposure, fundamentally altering the cellular response to damaging ionizing particles encountered in deep space. Beyond direct cellular modifications, bioengineering extends to engineered symbiotic relationships, introducing beneficial microbiota, genetically optimized to produce radioprotective compounds or scavenge damaging free radicals, could establish an internal defense network. This microbial shield would operate continuously, offering systemic protection without constant external intervention, functioning as a living, adaptable countermeasure. Furthermore, gene editing technologies like CRISPR-Cas9 offer precise control over genetic expression, allowing for the activation or deactivation of genes involved in cellular senescence or apoptosis in response to radiation damage. This targeted manipulation could prevent damaged cells from proliferating, thereby reducing the risk of cancer and maintaining tissue homeostasis during prolonged exposure. The practical implementation of these bioengineered solutions would likely involve pre-mission genetic therapy. Astronaut candidates would undergo procedures to introduce modified genes or beneficial microbes, integrating these protective elements into their fundamental biology long before launch. This preparation ensures the protective mechanisms are fully functional upon entry into the deep space radiation environment. Once integrated, these biological systems would operate autonomously, a living shield within the explorer. Enhanced DNA repair enzymes would continuously patrol the genome, correcting damage in real time. Boosted antioxidant pathways would neutralize oxidative stress, while specialized microbes would contribute their protective metabolites. This continuous, intrinsic defense contrasts sharply with passive physical shielding. Monitoring the efficacy of these bioengineered systems in space would involve advanced physiological sensors. Regular blood and tissue sampling would track gene expression, DNA integrity, and cellular health markers. These real-time diagnostics would provide critical data, allowing mission control to assess the astronaut's radiation tolerance and potentially adjust operational parameters or initiate further biomodulations. The system's resilience relies on its adaptability. While genetic modifications provide a baseline protection, ongoing research explores dynamic bioresponse systems where gene expression or cellular activity could be triggered by detected radiation spikes. This adaptive capacity would allow the astronaut's biology to optimize its defense mechanisms precisely when the environmental threat intensifies, conserving metabolic resources. Such intricate biosystems, however, introduce complex ethical and regulatory considerations. The long-term effects of genetic alterations and microbial integration in the human body within a deep space environment are largely unknown variables. Establishing comprehensive safety protocols and international bioethics guidelines is paramount before widespread adoption of these radical protective strategies. At a fundamental cellular level, these engineered defenses operate like an internal immune system against radiation. Upregulated repair enzymes ceaselessly scan DNA for damage, excising and replacing corrupted nucleotides. Concurrently, enhanced antioxidant pathways continuously detoxify reactive oxygen species, preventing widespread cellular inflammation and protecting vital organelles from free radical assault, sustaining cellular health. This intrinsic biological protection represents a paradigm shift from reliance on external, inert shielding. Instead of a bulky, static barrier, the astronaut's own biology becomes the primary defense layer, an active, dynamic system responding to the invisible threat. This integration of the human body as a living spacecraft component fundamentally alters mission architecture and resource allocation. The contrast with traditional physical shielding is stark. A meter of water or aluminum might attenuate some radiation, but it adds immense mass, requiring more propellant and engineering complexity for deep space travel. Bioengineering offers protection with negligible mass increase, directly enhancing payload capacity and mission range. It transforms the human body into a lighter, more efficient, and self-repairing vessel. Physical shields are static. Their protective capacity is fixed. Biological defenses, however, offer potential for adaptability. They can theoretically be modulated or boosted in response to varying radiation environments, such as during a solar particle event or prolonged GCR exposure. This dynamic response capacity provides a flexible defense, unmatched by any passive material barrier currently conceived. Despite these advancements, the inherent complexity of biological systems introduces new vulnerabilities. Unforeseen long-term interactions between engineered genes and the unique stressors of microgravity, altered circadian rhythms, or dietary changes in space could manifest as novel physiological challenges. The biological system, while robust, remains subject to the nuanced laws of organic chemistry. Furthermore, even enhanced biological repair mechanisms possess limits. Extremely high-energy GCR particles or prolonged, intense exposure could overwhelm these defenses, leading to accumulated damage that cannot be fully rectified. The theoretical threshold for bioengineered resilience against the most energetic cosmic events remains a critical area of ongoing scientific investigation. The maintenance of these sophisticated biological systems in deep space presents its own challenges. Ensuring the stability of genetic modifications, the vitality of symbiotic microbiota, and the continuous function of upregulated pathways requires precise nutritional support, controlled environmental factors, and potentially periodic biological rejuvenation therapies. This necessitates a proactive, integrated health management system. The very act of bioengineering introduces inherent risks. Unintended off-target effects of gene editing, unpredictable responses of genetically modified microbes, or the emergence of novel biological pathways under extreme space conditions could create unforeseen health complications. The precision required for these modifications is immense, yet the universe's variables are legion, demanding meticulous and cautious implementation. Moreover, the evolution of radiation itself poses a dynamic threat. While GCRs are relatively constant, intense solar particle events, coronal mass ejections, or even transient gamma-ray bursts, though rare, could deliver radiation doses far exceeding the engineered biological thresholds. Such extreme events could overwhelm even the most robust bioengineered defenses, leading to acute radiation syndrome despite cellular enhancements. The long-term viability of bioengineered traits in subsequent generations of space inhabitants is another critical consideration. While initial missions may involve modified individuals, the prospect of inheritable genetic changes for colonization efforts raises profound questions about genetic drift, selective pressures in space, and the potential for unintended evolutionary trajectories for humanity beyond Earth. Furthermore, a reliance solely on biological protection neglects the fundamental physics of the radiation environment. While bioengineering enhances individual resilience, it does not reduce the ambient radiation flux within a spacecraft. Habitats will still require some level of physical shielding to maintain equipment integrity and provide backup in case of biosystem failure or for non-modified crew members. Economic and resource limitations also play a role in the collapse of purely biocentric protection. The development, testing, and continuous maintenance of advanced genetic therapies and designer microbiomes are immensely expensive and resource-intensive endeavors. These costs could limit widespread implementation, favoring a hybrid approach where bioengineering complements, rather than entirely replaces, traditional shielding. Societal acceptance and regulatory hurdles represent a non-technical yet formidable challenge. Public perception of genetic modification, especially in the context of human spaceflight, could slow or halt progress. International consensus on the ethics and safety of altering human astronauts for deep space missions is indispensable for the widespread adoption and funding of these advanced protection methods. Finally, the concept of obsolescence applies even to biological engineering. As our understanding of cosmic radiation evolves and new biological insights emerge, current bioengineered solutions may become outdated. Continuous research and development will be essential to adapt and refine these protective strategies, ensuring they remain effective against an ever-unfolding understanding of the space environment. The vast, silent expanse of space continually tests the limits of biological endurance. The human form, adapted over millennia to Earth's specific protective conditions, faces an environment utterly alien to its evolutionary blueprint. Cosmic radiation, a fundamental aspect of the universe, reveals the delicate fragility of carbon-based life and the profound challenges of extending its reach. In the face of this omnipresent threat, bioengineering represents humanity's attempt to reconcile its biological limitations with its exploratory ambitions. It is a testament to the ingenuity that seeks to reforge the very essence of life, to imbue it with the resilience necessary to traverse the deep void. This endeavor pushes the boundaries of biological and ethical understanding, confronting fundamental questions of human identity. The universe cares nothing for biological vulnerability. Its physical laws are immutable. The ambition to colonize other worlds, to establish a multiplanetary civilization, hinges on mastering these laws. Bioengineering is not merely a medical intervention, but a foundational engineering discipline, modifying the most complex machine known, the human body, to function within an unforgiving cosmic context. Each solar flare, each distant supernova, reminds explorers of their vulnerability. Yet, each advance in bioengineering subtly shifts this balance, inch by infinitesimal inch. The human species, once confined by a planetary magnetic field, now contemplates a future where its very cells are designed to defy the cosmic torrent, a profound redefinition of biological destiny and cosmic interaction. The ongoing quest for cosmic radiation protection through biological means is more than a scientific problem. It is a philosophical statement. It declares humanity's intent to adapt itself to the universe, rather than merely shielding itself from it. This proactive biological transformation underscores a deep-seated drive to transcend terrestrial limitations and become true denizens of the cosmos. As the probes extend and the voyagers follow, the fundamental question persists. How far can biological engineering push the boundaries of human resilience? Can a modified biology truly assimilate with the relentless cosmic environment, or will the universe's sheer scale and indifferent power always dictate the ultimate limits of human endurance beyond Earth's protective embrace? The vacuum of space, silent and absolute, presents an immutable truth. Life, as known on Earth, is an anomaly, a fragile construct. To persist within this vacuum, life must either be meticulously shielded or fundamentally re-engineered. The path forward involves a deep understanding of radiation's interaction with matter, both inert and living, to rewrite the rules of biological survival. The evolution of life on Earth, billions of years in the making, crafted organisms perfectly suited for a protected planetary niche. Bioengineering represents an accelerated, directed evolution, an intentional intervention to fast-track adaptations that would otherwise require eons. It is a bold statement about humanity's capacity to resculpt its own biology for a future beyond its cradle. However, this ambition is tempered by the profound responsibilities that accompany such power. Altering the fundamental genetic code, even with the noblest intentions, carries the weight of unforeseen consequences across generations and ecosystems. The careful stewardship of these biological tools is as crucial as their development, ensuring ethical and sustainable progress. The vastness of the cosmos demands humility, yet inspires innovation. The challenge of cosmic radiation, though formidable, has spurred a scientific renaissance, pushing the boundaries of genetics, material science, and astronautical engineering. It forces a holistic view of space exploration, where the explorer is not just an occupant, but an integral, adaptable component of the mission itself. As the light of Earth fades into a distant star, the ultimate safeguard for its inhabitants will not just be the metal shell of their vessel, but the recoded resilience within their own cells. This intrinsic defense, honed by advanced science, promises to unlock deeper, longer voyages, redefining the very concept of human endurance in the silent, radiation-laced void. The fusion of biology and engineering offers a compelling vision. Explorers whose bodies are intrinsically aligned with the cosmic environment, minimizing the need for heavy, inert shielding. This integration represents a sophisticated harmony, where the biological system functions as an active, self-repairing component of the overall deep space exploration infrastructure. The silent pulse of a distant quasar, the slow drift of galaxies, these phenomena underscore the immense, indifferent scale of the universe. Against this backdrop, humanity's drive to protect its emissaries through bioengineering is a profound assertion of will, an attempt to bridge the vast evolutionary chasm between Earth and the cosmos. Ultimately, the success of bioengineering in safeguarding astronauts against cosmic radiation will determine the feasible range of human expansion. Will these biological modifications truly enable humanity to permanently settle celestial bodies beyond Earth's magnetic comfort? Or will the universe's inherent radiation always demand a fragile, temporary presence?